Okay, in this video I want to talk about the classic twin paradox. Page 60, volume 5, problem 37.7 kind of gives you the details. I'll just go over it really quickly. At some instant at time equals 0, Sophie is at rest in frame S, say sitting on the Earth, and Lucy in a spaceship goes flying by at speed beta. Okay, and for this problem, for no good reason, I set beta equal to 0.8. All right, so 80% the speed of light. So in frame S prime, Lucy is at rest and Sophie would be moving that way. Said another way, Lucy is at rest and sees the Earth receding far from her. And so now what's going to happen, I want Lucy to fly out to some star and then come back, right? So she's going to fly out or to some planet or something really far away and come back. And I want to consider what the world lines look like from Sophie's perspective. So let's take a second. If you want to try and draw this, right? So here's a space-time graph from Sophie's perspective. Event 1, Lucy leaves the Earth at time t equals 0. And here, Lucy returns at some later time. Okay, so pause the video, try to draw the world lines for this case, and if it helps, I'll just remind you really quickly, this was the information we saw. Remember, slopes on the world line correspond to 1 over beta, where beta is the speed, all right? Okay, let's go back to here. 3, 2, 1, here we go. So I'm going to start with Sophie. So from Sophie's perspective, Sophie remains at rest for however many years it takes Lucy to do this trip. So it's just basically a straight line up and down, right? So this black line here is Sophie. That's Sophie's world line. Straight up, she remains at the same, and remember in this case, I forgot to label the axis here. This axis right here is X, and this axis up here is CT. So X remains constant. What will Lucy's look like? Well, Lucy's booking Holland, and so what is 1 over, I'm just going to punch this in. 1 over this will be the slope. So 1 divided by 0.8, oh, that's probably pretty easy, that's 1.25. But then to do that, to get an angle, I'll tan inverse of that, 51 degrees. Okay, so about right there. All right, and then halfway, she's got to turn around and come back. So this whole thing is about yay tall. Somewhere right around here is where she'll turn around. So she's heading out to this star, and then at some point she's got to turn around. When she turns around, her x velocity should go to 0 and kind of come back here at about the same angle. Whoa. So that's my attempt to draw that. Let me make sure that shows up. All right. And so remember the slope here. All right. So now I have 2 more questions. Who's going to age more rapidly? Right? So the contradiction or the paradox is this. From Sophie's perspective, right, Lucy is moving clocks run slow. Lucy should age less. From Lucy's perspective, Sophie is the one that's moving, and so Sophie should have the moving clock, it should age less. So there's lots that goes into this, a very simplistic version of answering this question, why it's not a paradox. Look, does Lucy maintain constant velocity? No. We see that Lucy has to reverse direction to come back. And so if Lucy has to reverse direction and come back, her velocity's not constant. No, special relativity does not apply. This is not a contradiction. This is the simplest way to try and explain this. And so we see that Lucy is not bound by, or she's not in an inertial reference frame because her velocity is not constant. And it turns out, we'd say Sophie ages more rapidly. And there's tests that have been done for flying cesium clocks, right? Moving cesium clocks versus clocks that are at rest. And we can do this test, and it actually has been verified experimentally. Sorry, I'm yawning there. Long day. So the moving clock runs slow, meaning Lucy ages less, and it's not a contradiction. And so maybe seeing the world lines is, this is one good example of that. The pole and the barn paradox, the next one, 37.8, you should try that now. It's a little bit more complicated and you're trying to draw these world lines, but I'm gonna leave that one for you. All right, so let's call that good.